Welcome to Lecture 35. In this lecture, we want to begin to talk about the Bernstein-Vazirani algorithm. And in Lecture 35, we'll talk about the classical version of this algorithm. And we will also talk about some preliminary results that we will need in order to understand the quantum version of this algorithm, which we will discuss in Lecture 36. So the Bernstein-Vazirani algorithm has the following idea. We have U, which is a string maybe I should begin by saying unknown string of n bits. And we have a function f sub u which acts in the following way. If you have an input q to f sub u, and by the way, q is a known query string of n bits, and f sub u of q is equal to q dot u modulo 2. Now, first of all, just to make sure that everybody understands what modulo 2 means, modulo 2, let's say that we have something like, suppose, let's say m is an integer, then m modulo 2 is simply the remainder when m is divided by 2. So if m is even, m modulo 2 equals 0, and if m is odd, m modulo 2 equals 1. And these are the only two possibilities. If you were talking about modulo 3 arithmetic, then there are three possibilities, 0, 1, and 2. If you were talking about modulo 4 arithmetic, there would be then four possibilities, 0, 1, 2, and 3. But for modulo 2, there's only two possibilities, 0 and 1, and if something is even, then if m is even, then m modulo 2 is 0. If m is odd, then m modulo 2 is 1. So we come back up here now to our information about the Bernstein-Vazirani algorithm, and you see that the situation we have is that we have this unknown string u. We would like to figure out what u is equal to, and as is stated, it has n bits, and so we can use this function f of u and different query strings to try to find out what u is. But the way that f sub u works is that if you give f sub u as an input, if you give it some query string, then what f sub u will do is it will compute q.u, and remember q.u is simply equal to the number of positions in which the string Q and the string U both have a 1. And then once it computes that value, it won't tell you that value, but it will then divide that value by 2, and it will tell you the remainder. So basically, you can think of it like this. If you have as input to F sub U some string of n bits, F sub U, the output then will tell you whether that string and the unknown string U have an even or an odd number of positions in which both of them have a value of 1. So just to make absolutely sure this is clear, let's suppose U is equal to 10101. And so you can see here that n is equal to 5. That is the length of the string U. And but again, suppose that string is unknown. You may know it, but somebody else is trying to guess it, and so they might have a query string equal to, let's say perhaps 11100. Their query string will have the same number of bits as the unknown string, and so at least they know that much, how many bits there are. And so let's say that they had the query string 11100. Then the value of F sub U in this case, F sub U of Q in this case, let's say maybe write this a little differently. In this case, F sub U of Q is equal to 0. Now let's make sure we understand this. If we compare U and Q, the number of positions in which both of them have a 1 is 2. They both have a 1 in the first position, and they both have a 1 in the third position. So the number of positions in which they both have a 1 is 2, and 2 mod 2 is equal to 0. That is, when you divide 2 by 2, you have a remainder of 0. Or another way of saying it is 2 is an even number. However you wish to look at it, you end up with the result that F sub U of Q is equal to 0 in this case. On the other hand, if let's suppose that again U is equal to 10101, so that n is equal to 5, and this time let's suppose that Q is equal to 10010. Well, in this case, we see that F sub U of Q is equal to 1, because Q and U both have a 1 in the first position, but there's no other position in which they both have a 1, and therefore the number of positions in which they both have a 1 is just 1, and 1 modulo 2 is 1, so in this case F sub U of Q is equal to 1. So now, given that is the way that the function F sub U of Q works for different query strings, I extremely strongly encourage you to turn off the video for a moment and think about this question. How could you find out U using this function. Actually, let me rephrase this just a little bit. How could you find out an unknown string U using this function? How many queries would you need? In other words, how many times, or for how many different queues, for how many different query strings would you need to evaluate f sub u of q before you would be certain of the value of the string u? So I strongly encourage you to stop the video for a moment and think about that and try to find what you would consider to be the most efficient algorithm that you can find to find u with certainty. And then when you think you have it, turn the video back on and compare. Okay, well, I hope that you were able to give that problem some thought. And certainly there's not a unique way to do this, but I believe that you will be hard-pressed to find, in fact, I think you will not be able to find any solution to this problem that would allow you to find u with certainty with fewer than n queries. And let me show you one possible approach. Okay, let's say query 1. You could have 0, 0, 0, dot, 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 0. And then in the very last position, you have a 1. Now, if you query with that string, that is going to tell you for sure what value u has in that last position. Because let's say it like this. If you query, so this is q. If you query with this q, then you will know that the last bit of u is 1 if f sub u of q is equal to 1, and that the last bit of u is 0 if f sub u of q is equal to 0. Because, and probably you all already understand this, but just to make sure, see, since this string, this query string that we're using here, has zeros everywhere except in that last position, then the number of positions in which both q and u could even possibly have 1, since there's only one 1 in q, then the only possibilities for the number of positions in which u and q both have a 1 is either 0 or 1. If u has a 0 in that last position, then U and Q don't have any positions in which they both have 1. So in that case, F sub U would be 0. But on the other hand, if U has a 1 in that last position, then U and Q would have a 1 in exactly one position in common, and therefore F sub U would be equal to 1 in that case. So by using this query string as our first one, we can find out whether or not U, or whether U has a 1 or a 0 in that last position. And of course, once you've seen that, I think you can guess the others. And of course, you actually don't have to do this in any particular order, but to be systematic, I will. So the next one we can say 0, 0, 0, dot, 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 0, 1, 0. Now we have a 1 in the next to last position of Q. And this will allow us to find out whether U has a 0 or a 1 in its next to last position. And we keep on trying different Qs. Each Q we try will have all zeros except for 1 in just one position. And this will allow us, after n queries, to determine the value of all of the n bits of the unknown string 1. So this classical approach requires n queries. And I'll put here dot, dot, dot. So that requires n queries. And so obviously, if you have a very long unknown string, then you will have quite a large number of queries that you will need to make before you can determine what that unknown string is. And so the question, of course, and I'm sure you're used to this by now, the question is, can we find an algorithm that employs the ideas of quantum computing to determine this unknown string in fewer than n queries? And the answer is yes. Actually, with the Bernstein-Vazirani algorithm, we will only need one query using an entangled state in order to determine the unknown string U. So that's what we have to look forward to in the next lecture. But in order to understand everything in that lecture, we will need a couple of preliminary results. And so what we will do now is spend a few moments, we'll say now, let's consider some preliminary results that will help us to understand the Bernstein-Vazirani algorithm in lecture 36. Okay, the first preliminary result. Right. Okay, the first preliminary result that we would like to consider is the following one. It says that -1 to the U dot Q plus Q plus Z dot Q power is the same as -1 to the U exclusive or z dot q. And remember now what we're talking about: u, z, and q are all streams of n bits. And u exclusive or z is understood to be bitwise. In other words, if u is equal to u n minus 1, u n minus 2, dot, 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 u1, u0, and z is equal to z n minus 1, z n minus 2, dot, 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 z1, z0, where, of course, all of these un minus 1, un minus 2, dot, 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 u1, u0, zn minus 1, zn minus 2, dot, 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 z1, z0, all of those are either zeros or ones. And so, by u exclusive or z, what we mean is a string whose first bit is un minus 1 exclusive or z n minus 1. And then the second bit would be un minus 2 exclusive or z n minus 2. Dot, 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 down to u1 exclusive or z1 and u0 exclusive or z0. So as an example, let's suppose n equals 4, and maybe u is equal to 1, 1, 0, 1, and z is equal to 0, 1, 0, 1. So in this case, u exclusive or z would be, okay, we look at the first bit in each one, and those two are different, and we know that the exclusive or of two values that are different will be 1, and the exclusive or of two values that are the same will be 0. So the exclusive or of 1 and 0 is 1. The exclusive or of 1 and 1, since those are the same, that will be 0. The exclusive or of 0 and 0 will be 0, and the exclusive or of 1 and 1 will be 0. So if u is 1, 1, 0, 1, and z is 0, 1, 0, 1, then u exclusive or z is 1, 0, 0, 0. So now that we understand the notation, let's get back to this first preliminary result right here and try to understand why it is true. Why is it true to say -1 to the u dot q plus z dot q is equal to -1 to the u exclusive or z dot q? That's our question. And to understand this better, let's maybe write it out like this. -1 to the u dot q plus z dot q is equal to -1 to the u n minus 1 q n minus 1 plus u n minus 2 q n minus 2 plus plus u1 q1 plus u0 q0. Now that takes care of the u dot q part, and then we also have to include the z dot q part. So plus z n minus 1 q n minus 1 plus z n minus 2 q n minus 2 plus plus z1 q1 plus z0 q0. Now, if we think about that for just a moment, we see that the okay, let me maybe just emphasize these first n terms come from u dot q, and the second n terms come from z dot q. Well, if we look at the first term from each of these sums, the un minus 1, qn minus 1, and zn minus 1, qn minus 1, then we see that this could be grouped together to give un minus 1 plus zn minus 1 qn minus 1 plus un minus 2 plus z n minus 2 q, wait, this should be n minus 1, and then this will be q n minus 2 plus plus u1 plus z1 q1 plus u0 plus z0 q0. That's just a matter of rearranging these two n terms that we have here, up here, these two n terms in the exponent of -1. We have just rearranged them and then factored the different pairs. Now, let's look at each one of these terms now in the exponent. Okay, let's first of all make the observation that we could, at this point, write this in the following way. We have un minus 1 plus zn minus 1 qn minus 1, and then times -1 to the un minus 2 plus zn minus 2 qn minus 2 times times -1 to the u1 plus z1 q1 times -1 to the u0 plus z0 q0. We know that that's just the way that exponents work, and so we could break this up into these terms. And now if we look at these terms, we'll quickly see a pattern going on here. Let's look at this first term right here. -1 raised to the un minus 1 plus zn minus 1 times qn minus 1 power. Now notice that if un minus 1 and zn minus 1 are both 0, then of course the entire exponent for this term becomes 0, and we would get -1 to the 0th power, which would be 1. So this term is equal to 1. Actually, I guess I'll put it like this. It'll be equal to negative 1 to the 0th power if un minus 1 equals zn minus 1 equals 0. And it's equal to negative 1 to the first power. Actually, it's equal to negative 1 to the qn minus 1 power if un minus 1 equals 1 and zn minus 1 equals 0, or un minus 1 equals 0 and zn minus 1 equals 1. And that's pretty clear. No real magic there, because if all we're saying is that if this sum here is equal to 1, then this is negative 1 to the 1 times qn minus 1 power, or negative 1 to the qn minus 1. And of course, the way that this parenthetical term can be equal to 1 is if un minus 1 is 1 and zn minus 1 is 0, or if un minus 1 is 0 and zn minus 1 is 1. But now the interesting observation comes in this last case where they could both be 1. If both of these are equal to 1, then this parenthetical term is 2, and 2 times qn minus 1 has to be an even number. It doesn't matter what qn minus 1 is. 2 times qn minus 1 is an even number, and negative 1 raised to an even number is equal to positive 1. So therefore, this is the same thing as negative 1 to the 0th power if un minus 1 equals zn minus 1 equals 1. And so now you see the key to this. We can summarize all this in this fashion by saying negative 1 to the un minus 1 exclusive or zn minus 1 times q n minus 1. And notice how that works. It's just saying that if un minus 1 and zn minus 1 have the same value, whether that value is 0 or that value is 1, it doesn't matter, because if they have the same value, then we want to multiply. We want to have negative 1 to the 0th power. And if we put exclusive OR here, that will work in exactly that way. And on the other hand, if un minus 1 and zn minus 1 have different values, then this exclusive OR will give us 1, and we'll have 1 times qn minus 1, which would just give us qn minus 1 on the top. So this is a convenient way to summarize all of this information. And of course, then the next term would be negative 1 to the un minus 2 exclusive OR zn minus 2 times q n minus 2 negative 1 to the u1 exclusive OR z1 times q1, and then finally negative 1 to the u0 exclusive OR z0 times q0. And now, if we put all those back together, we get negative 1 to the un minus 1 exclusive OR zn minus 1 qn minus 1 plus un minus 2 exclusive OR zn minus 2 qn minus 2 plus plus u1 exclusive OR z1 q1 plus u0 exclusive OR z0 times q0, which of course could be written more compactly simply as -1 to the u exclusive or z dot q. And so that verifies our first preliminary result. And this will come in handy to us when we're dealing with the quantum version of the Bernstein-Vazirani algorithm. Now there is a second preliminary result that we would like to consider, and it is the following. Suppose y is a fixed string of n bits, then the claim is this, that the sum x equals let's just say x is any member of the standard basis for n-qubit states so it could be n zeros or n-1 zeros and a 1. I mean, any, in other words, it's basically any string of n bits where we look at over all possibilities. Each one of them could be a 0 or a 1. So since there's 2 possibilities for each of those n qubits, and there's, like say, n of them all together, then there's 2 to the n different possible values for x that we are assuming. And actually, the way that your book is writing this is a little bit different, so I'll show you that as well. So anyway, so the preliminary result we want to prove is, or consider, is this: to the -1 to the x dot y. This is equal to 2 to the n if y equals 0 and it's equal to 0 otherwise. Now the way that your book is actually writing this is just this. They say sum x equals 0 to 2 to the n minus 1 of and then -1 to the x dot y equals 2 to the n if y equals 0 and 0 otherwise. And you have to understand what this notation means. It's just saying that x is an n qubit state, and that this bottom 0 actually means n zeros, and we're going to look at all of the values between 0 and 2 to the n minus 1, and those expressed as binary numbers would give you the different entries in the qubit in the n qubits of the state. So however you wish to write this summation, they mean exactly the same, but this is the second preliminary result that we will find useful in the quantum version of the Bernstein-Vazirani algorithm. And so I encourage you to take a moment first. Now remember, this is y is a fixed string of n bits. So x is varying. We're looking here over different values of x. But then when we sum up what we get for all of these 2 to the n values of x, we will get 2 to the n if y is equal to 0, but otherwise we will get 0. And so think about that for a moment and see if that seems reasonable to you. And then when you think it is clear, turn the video back on and let's see if we all see eye to eye about this statement. Okay, so I'll tell you at least my thinking about this problem, and you can compare it to yours. First of all, the top claim that this is equal to 2 to the n if y equals 0, well, that's, to me, that seems to be pretty obvious, because if y is equal to 0, now remember again, that means that actually that's the n-qubit state that has all zeros. Well, if y is equal to that state with n zeros, then x dot y is clearly just equal to 0, because remember that, again, x dot y is equal to the number of positions in which x and y both have a 1, but if y is all zeros, then obviously x dot y is 0, and so then negative 1 to the x dot y power would be negative 1 to the 0 power, or 1, and 1 summed up, as we pointed out a moment ago, the total number of terms in this summation is 2 to the n. So if we sum up 1, 2 to the n times, we get 2 to the n. So the top result is, I think, pretty clear. But how do we get the bottom result? Well, the way that I look at this is to look at it, look at the terms that appear in this sum in pairs, and we'll see that each one of these pairs goes to 0. Let me show you what I mean by that. So let's suppose, we'll keep this simple, let's suppose maybe that n is equal to 3 and y is equal to perhaps 1, 0, 1. Okay, and I'll show you why I think that this the bottom expression, of course, the bottom expression is the one that would apply in this case, because y is not equal to 0. So we're claiming that if y is anything other than 0, then this summation will end up being equal to 0. And so let's see why. Now, as I say, I think that if you look at this pairwise, you'll see why. And I'll show you what I mean. Okay, so x, since n is equal to 3, 2 to the n is 8, minus 1 is 7. So we want to look at x equals 0, 1, 2, 3, 4, 5, 6, 7. And so we have basically these possibilities. X equals 0, 0, 0, and 0, 0, 1. That's one pair I want to consider. And then 0, 1, 0, and 0, 1, 1 is another pair. 1, 0, 0, and 1, 0, 1 is another pair, and then finally 1, 1, 0, and 1, 1, 1. So I'm going to break up, and notice, of course, that the first two are 0 and 1, 2 and 3, 4 and 5, and then 6 and 7. And now let's see how this works. Okay, if we take if we look at what the contribution to the sum will be for each one of these, okay, for x equals 0, 0, 0, well, x dot y in this case is 0, and so we would have negative 1 to the 0 power, and we'll get a contribution of 1 to the sum for that one. Now for the next one, 0, 0, 1, well, that x dotted with y is equal to 1, because this x, the 0, 0, 1, and y, which is equal to 1, 0, 1, they agree, they both have a 1 in that last position, and therefore x dot y is equal to 1. They both have 1s in exactly one position. So x dot y is equal to 1, and negative 1 to the x dot y would be negative 1 to the first power, or negative 1. And we see how those two pairs, the contributions from those two pairs cancel each other out. And the reason that that happens is that these two pairs differ, the 0, 0, 0 and 0, 0, 1 differ in only one position. And we're going to see that, and that's true, of course, for each one of these pairs. They differ, the two values for x differ only in one position. And so always one of them will give us one value, and the other one will give us the negative of that value, and they'll always cancel out. But let's go ahead and proceed with this. Okay, so when x is equal to 0, 1, 0, Then x and y don't have any ones in the same position, so x dot y is 0, and negative 1 to the 0 is 1. So we'd get a contribution to the sum equal to 1 in that case. But when x is equal to 0, 1, 1, then x dot y is equal to 1, because they both have, x and y would both have a 1 in the last position. And so x dot y is 1, and negative 1 to the x dot y is negative 1 to the first power, or negative 1. And again, those two contributions to the sum will cancel out. Now let's go to the next x, 1, 0, 0. X dot y here is equal to 1, because they both have a 1 in the first bit. And so they agree, they both have a 1 in one location, so x dot y is 1, negative 1 to the 1 is negative 1. So we get a contribution to the sum of negative 1 in that case. Now what about for the next x? 1, 0, 1 and 1, 0, 1. Those dotted with each other gives us 2. Because there are two positions in which both have a 1. They both have a 1 in the first position. They both have a 1 in the last position. So x dot y for this is equal to 2, but negative 1 to the 2 power is 1. And so again in this one, the two contributions to the sum cancel each other. And now let's do the last pair, 1, 1, 0. That x, 1, 1, 0, and y both have a 1 in only the first position, and therefore x dot y is 1, and negative 1 to the 1 power is negative 1. And for 1, 1, 1, that particular x and our given y have 1s in both the first position and the last position. So therefore, they both have 1s in two positions. So x dot y is 2, and negative 1 to the 2 power is 1. And so sure enough, we see that when you look at the analysis in this way, the pairs will always give contributions that cancel each other. And so that's why this sum is equal to 0 if the fixed string y has any value other than 0. So those are all the preliminary results. Everything else we need to understand the quantum Bernstein-Vazirani algorithm we have already covered. We just needed to cover those two additional results, and now in the next lecture we will be able to cover the Bernstein-Vazirani algorithm in a straightforward fashion with not too much delay. Since the ideas here in this lecture have been so straightforward, I really don't believe it's appropriate to worry about trying to make a problem testing these ideas. We'll wait until we've covered the entire Bernstein-Vazirani algorithm, the quantum version of it, in lecture 36. So for the problem for this lecture, let's just have a review problem. This is one that you've seen in a previous quiz. I'm not going to tell you which one, because I don't want you to spend a lot of time going back through notes. I want you to see if you can recall how to do a problem like this. So anyway, we have this quantum circuit shown, and you're told how A acts on 0, the 0 cat, and the 1 cat. And so given that information, you want to find the matrix for this circuit. And that is, let me make sure you understand this. This is the matrix relative to the standard basis. And by the way, let me color this in, because this is from a quiz that we did before we were using this more recent notation. And so let's color this in, and when we color it in, what that means here, just to make sure you understand and recall, if the qubit on the second line here is equal to 0, that 0 will pass right on through, and whatever qubit is on the first line will also pass right on through. Both of them will pass through undisturbed if the qubit on the bottom line is 0. But if the qubit on the bottom line is equal to 1, then the qubit on the top line will be toggled. So if the qubit on the top line is 0 to the left of the ax, it will become 1 to the right of the ax. And on the other hand, if it is 1 to the left of the ax, then it will become 0 to the right of the ax. Again, though, the 1 on that second line would pass right through. So that's the way that the different elements in this circuit act. And by the way, also up here, same thing here. If the qubit, or whatever qubit comes into this dot here, that it will pass through, but that controls this A. So in other words, the qubit on the second line will pass right through and not be changed by this box at all if the qubit on the top line coming in is 0. But if the qubit on that top line is 1, then the qubit coming in here will be influenced by A, and the way that A acts is as given right here. A of 0 is equal to C0 plus D1. A of 1 is equal to D0 minus C1. So given that information, find the matrix relative to the standard basis for this circuit. And that's the only problem for the lecture part of lecture 35. And then we'll have another problem, probably also of a review nature, in class. So that concludes lecture 35, and good luck.